All right, so what I have here is an RLC series circuit. So in this circuit, I have one resistor, two inductors, and two capacitors. So the main thing that we're focused on right now is just finding Z. So what I'm wanting to do is find impedance. Okay? So if you break it down like this, it's really easy. So maybe I give you a circuit and you have to come up with a couple of these values. That's fine. But once you find these values, then you'll be able to solve for Z. And we'll get into the more complex stuff later. But for now, let's just start out with finding some of our totals. So we're starting out with impedance. So remember, the formula that I'm going to be using is Z equals the square root of R squared plus parentheses XL minus XC squared. So the objective is to find a resistance total, an inductive reactance total, and a capacitive reactance total. Okay? So let's think back to our rules of a series circuit when we're thinking about ohms. Because remember, all three of these are part of that impedance triangle, which is going to be measured in ohms. So when you're solving these circuits, even the more complex ones, just remember that resistance, inductive reactance, and capacitive reactance are all treated equally as far as Ohm's law goes. So if you have voltage and current, do voltage divided by current, and that'll give you every one of these individual values. Okay? So let's just focus on breaking this down and getting impedance first. So remember, impedance is the total current limiting property in this circuit. So when I have this resistor, these inductors, and these capacitors in this circuit, the total current limiting factor of the whole thing is impedance. Okay? So what we want to do is we want to start out and we want to break it down. So let's look and find resistance total first. So how many resistors do I have? I have one. So obviously resistance total is just going to be 300 ohms. Alright, so our rule for series circuits with resistance and ohms is they simply just add up. So to find my XL total, my inductive reactance total, I have an XL1 of 75 ohms and an XL2 of 400 ohms. Okay? So my XL total is going to be 475 ohms. Okay? And now I just do that with the XCs. I have two XCs. One's 100 ohms and one is 300 ohms. So 100 ohms and 300 ohms in series with each other is 400 ohms. Okay? So now all I have to do is plug these numbers into this formula here. Okay? So that's going to give me Z is equal to the square root of 300 squared plus parentheses 475 minus 400 squared. So essentially, take the difference between these two, and all it really is 75 squared there. But think about this for a moment. What if I did not have this capacitor in here? That would be 475 squared as opposed to 75 squared. So that would have gave me a really huge angle. Because think about it, if we plotted that as a triangle, I would have 300 here, and I would have 475 going way up here. And then I'd connect those, and that's the impedance. But now what I have done is I have added 400 ohms of capacitive reactance. So this side of the triangle is actually only 75. So really, this triangle now actually only looks about like that. So see what I did? Voltage and current are no longer that far out of phase with each other, which is going to mean smaller angle, better power factor. Okay? So in the calculator, you're going to do 300 squared plus parentheses 475 minus 400, close parentheses, squared, hit your equals button, and then square root that. And you should have 309.23. So Z equals 309.23 ohms. Okay? So that's very simple, very basic. All right? This formula looks a little intimidating, but it's not when you break it down into the individual totals. Okay? And you can even go ahead and subtract this and then put it into your calculator even easier. So you can just do 300 squared plus 75 squared equals, and take the square root, and you get the same thing, 309.23. So whether you want to put the whole thing in your calculator, or if you want to go ahead and do your subtraction, and then instead of 475 minus 400 squared, you would just have 75 squared here. Okay? So, as simple as that, and that's all there is to find an impedance. Doesn't matter if I had 10 components in here. You're always just going to combine all of your likes, get your individual totals, and then plot it into your formula. Okay? All right. So, with that being said, let's go ahead and give this a current. Okay? So I want to make sure everybody's caught up. All right? So if you need to pause, think about this for just a second, rewind back, solve these again, then go ahead. All right? So now, what we're going to do is we're going to look at the voltage triangle. Okay? So I'm going to go ahead and erase these. And we're going to look at the voltage triangle. So I chose one of these ohm values to prove a point. All right? Because a lot of people get stumbled up on this because it looks very weird. And you're like, this can't be right. But it is. Okay? So what I'm going to do is I'm going to give a current total of 2 amps. So remember, this is a series circuit. So what does that mean? If IT is 2 amps, that means that IR1 is 2 amps. IL1 is 2 amps. IL2 is 2 amps. IC1 is 2 amps. And IC2 is 2 amps. Okay? Because current stays the same everywhere. So now, remember ohms and amps. So in order to get the voltage drops around this circuit here, all I have to do is my Ohm's law formulas. So I'm going to have either V is equal to R times IR, so current times resistance, or I'm going to have, so I'll call that VR, VL, so voltage across the inductors, is going to be XL times IL. And then VC is going to be XC times IC. So if you look, it's all the same formula, just different different components in there. V equals R times I, or I times R. VL is XL times IL. VC is XC times IC. So it's all still your ohms times your current gives you voltage. Okay? So let's go around and let's find our voltage drops. Okay, so I chose 2 amps because we don't even need a calculator for that. So let's look here. Okay, so we have 300 ohms and 2 amps. So that's going to give me a VR1 of 600 volts. And then I'm going to look at the inductor. 75 times 2 would give me VL1 of 150 volts. Then I have XL2 is 400 ohms. 400 times 2 gives me a VL2 of 800 volts. And then across the capacitors, 100 times 2 gives me a VC1 of 200 volts. And then VC2 is 300 times 2 is 600 volts. Okay? Draw a box around these so that way you can don't get them confused. Okay. So that's essentially what I have. I don't know if that made that more confusing or what. Drawing the boxes. Alright, but let's just look at what we have. So we're going to have to get a VR total, a VL total, and a VC total. Since we have multiple components, we want to add up all of our like voltages. So we only have one resistor, so that means that 600 volts. Okay? Because VR1 is the only VR, so it's 600 volts. Now I have 2 VLs. VL1 is 150, VL2 is 800. 800 plus 150 is 950. So VL total is 950 volts. Okay? Now, let's look at the 2 capacitive voltages. I have 200 and I have 600, so that's going to be 800 volts. So I have a VR total of 600 volts, a VL total of 950 volts, and a VC total of 800 volts. So remember, on the previous video, alright, the voltage formula, the voltage total formula is going to look a lot like the impedance. So I'm going to have V total is equal to the square root of VR squared plus parentheses VL minus VC squared. And that's going to give me the total voltage. So now all I have to do is use these values here and then plug it into the formula here. So I have V total is equal to the square root of 600 squared plus parentheses 950 minus 800 squared. Just a pointer. Remember, there's parentheses here. This is not 800 squared. This is this set of parentheses squared. right, so let's do that in our calculators. So I have 600 squared plus parentheses 950 minus 800 close parentheses and squared, hit equals, and then square root it. And that gives me 618.47 volts. Okay? So, V total is equal to 618.47 volts. And again, you could do your subtraction in here if you wanted to, okay? So that is completely up to you, all right? So you could do 600 squared plus, the difference between these two is 150 squared equals, take the square root, and I get 618.47. So, this is what I wanted to show you. When you have inductors and capacitors in the same circuit, your inductors can actually induce a voltage higher than your source. Think about it. Total voltage, which is this source here, is 618.47 volts. Well, VL2 is 800 volts. I'm almost 200 volts higher across this inductor than what total is. And that's okay. Remember, this is just a magnetic field inducing a voltage. Okay? Inducing a CMF. That just means CMF is really high across this inductor here. Okay? So it is not out of the normal to have a voltage across one of your inductors that is actually higher than the source. Because remember, capacitance's job is to subtract. Okay? It's to subtract from that inductance. So it's 950 minus 800. So that side of that triangle is only 150, not 950 or 800. Okay? So, I hope that made sense. Alright, so that's all the videos for now. So what I'm going to do is I'm going to upload some worksheets. And those worksheets are just going to be kind of honed in on calculating some total voltages and some impedances. And then the next video, we're going to expand and do our power triangle. And then we're going to solve a whole circuit. Okay? Alright, so if y'all have any questions, be sure to reach out in the group chat or email me, whichever you prefer. So again, been a pleasure. Hope y'all have a great rest of your day or night. Thanks.